Okay, so welcome again to the new lecture. This is lecture number 26 of phase equilibria course. So we'll first recap the contents of the last lecture. So in the last lecture we looked at how to calculate the phase fractions in a binary eutectic system, especially concentrating at hyper-eutectic composition. So we correlated the components of different phases, and then we looked at few example phase diagrams. So we looked at copper-nickel, which was the isomorphous system. So we looked at how the microstructure of a copper-nickel system looks. It does not look like a perfectly homogeneous system. It looks like a micrograph showing some contrast, which is basically due to compositional contrast. And then we looked at aluminum silicon system, which makes a eutectic system. So this is isomorphous, and this is eutectic, which although it makes a eutectic system, there is very little solid solubility at lower temperatures, and as a result the mixture is basically aluminum and silicon. Well, silicon being present in morphology which is deleterious to mechanical properties. As a result, the refiners always microstructural refiners are added to improve the morphology of silicon so that alloy can have better mechanical properties. In this lecture we will look at some more alloy systems of commercial importance and see what kind of reactions they possess and what kind of microstructures that we obtain in those systems. So the examples that we will look at in this first example is lead tin system, which is a eutectic system. So let's see how it looks like. So this is lead tin phase diagram. It's a binary eutectic phase diagram with considerable solid solubility at eutectic temperature. So lead is FCC, tin is has a different crystal structure, which has different crystal structure as compared to tin. They make two solid solutions, alpha and beta, for lead rich and tin rich ends. Lead rich side has considerable solid solubility at eutectic temperature, about 18.3%, whereas the solid solubility of lead and tin is very little, it's about 4 to 5%. As a result, it makes the beta phase, which has very little solid solubility at lower temperatures, but reasonable solid solubility at high temperature. They have a eutectic mixture at 61.9% tin, which eutectic mixture converts directly into alpha and beta phases, and they have this terminal solid solubilities of 18.3% at high temperature. So eutectic temperature is 183 degrees centigrade. At eutectic temperatures the solid solubility is 18.3%. This is, I think, about 95%. Let me see. Sorry, yeah. So the region which is between this 18.3 and 61.9 is called as hyper-eutectic region, whereas the region between 61.9 and let me just, it's about I think it's about 96% roughly. I may be wrong, but it's in this range. So between this 61.9 and this point, the alloy is called as hyper-eutectic. So of course, so we'll show you how three microstructures look like. So we'll look at microstructures in the three. So we'll look at microstructure which is of hyper-eutectic, eutectic and hyper-eutectic. Okay, so these are the three compositions. So hyper-eutectic alloy is of composition 58% tin. Eutectic composition is of 61.9% tin, and hyper-eutectic basically is of high composition, roughly perhaps about 80% or 90% tin. So what we have here is we have in the hyper-eutectic phase diagram, you can in the microstructure you can see that if you draw a line somewhere here, 50% is this line. Okay, so you can see that you have pro-eutectic pro-eutectic alpha present at this point. So what we have is, let me just change the ink color, maybe the green one. So at this point we have pro-eutectic alpha, and at this point this pro-eutectic alpha and liquid must have been there, liquid of this composition. This liquid transforms into mixture of alpha and beta. So what you have, this lamellar structure where you can see this parallel white and black plates at various places. This is all eutectic. So this is eutectic mixture of alpha and beta present along with hypoeutectic alpha. So you can find out the proportions in the manner I explained earlier. So you can see that this alpha phase is of the, so this is 175 micron. So you can see that this alpha phase is nearly, it's about 20-30 microns or so, whereas the size of constituents in the eutectic is far smaller, which is basically because eutectic converts into solid all of a sudden. As a result, phases don't have too much time to grow, and since phases don't have too much time to grow, the phases are finer as compared to the pro-eutectic phase. So alpha and beta sizes are lower, smaller as compared to pro-eutectic phases in the hypo or hypereutectic. So similarly, if you look at hypereutectic region, you have pro-eutectic beta along with eutectic phase. So this is the eutectic phase. Again, you can see that the size of beta phase is smaller as compared to pro-eutectic phase. So hypo and hypereutectic microstructures are fairly similar, except that the pro-eutectic phases are alpha in one case and beta in another case. Whereas in the eutectic phase image for this composition, so this is for hypoeutectic alloy. For eutectic composition, you have only 6 eutectic phase. So what you have is only the parallel plates of alpha and beta. So what you have, this is, so you can say that this black one is alpha and the gray one is beta, and these alpha and beta grow together and they form these colonies. So essentially, if you look at microscopically, alpha and beta grow in this fashion. Okay, so let's say one of them is, so let's say this is alpha, and the other one is beta. And remember, alpha is lead rich, which means it has to reject tin. Beta is tin rich, it has to reject lead. So partitioning of solute has to happen, which means tin needs to travel this side and lead needs to travel this side. As a result, simultaneous growth and simultaneous solute partitioning has to happen. There is not enough time for this to happen. As a result, the eutectic is generally finer mixture as compared to the pro-eutectic alpha or beta. So this is a microstructure that you are likely to observe in case of a eutectic mixture of lead and tin. Now let's come to next important alloy, which is of commercial importance, which is so the next one is iron carbon system, and this is a complex phase diagram. It has peritectic, it has eutectic, and it has eutectoid reactions. Okay. So this is how, so again this is the zoomed up image of microstructure of eutectic composition. So the eutectic shows the parallel lamellas of alpha and beta, whereas this is the hypoeutectic alloy, 50% tin, 50% lead. So you can see that alpha, which is alpha phase, which is the lead rich phase, is pro-eutectic phase, and then you have a mixture of alpha and beta as eutectic. Now this is the celebrated iron carbon diagram. Now this is generally iron carbon diagram is from 0% carbon to 6.7 weight percent carbon. Basically 6.67 weight percent carbon means Fe3C. So essentially it's Fe3C phase diagram, and Fe3C consists of 6.7% carbon in weight wise, So it's from 0 to 6.7% carbon region phase diagram. Okay. So what this phase diagram has is, it has multiple regions. You know, carbon has different structure, different atomic radius as compared to iron. As a result, they don't have complete solubility in various forms. Carbon and iron also react to form an intermetallic compound called as Fe3C. So if you have 6.78% carbon, it will make Fe3C compound. So everything will be 100% Fe3C. So what it has is, it has three regions. The first region is this peritectic region, which is at carbon compositions lower than 0.5%. Okay. Then we have so this is at 1493 degrees centigrade. Then we have another region at 1147 degrees centigrade. In the vicinity of this temperature, starting from 2.1% to 6.7%, we have this region called as eutectic region. And then at lower temperatures, at 727 degrees centigrade, the phase of the gamma phase of iron transforms into alpha plus cementite, which is Fe3C, at a composition of 0.676. So we have this as a eutectoid region. So there are three regions of the phase diagram: the peritectic region, the eutectic region, and the eutectoid region. And these are three invariant reactions that occur in iron carbon phase diagram. So let's look at each of these regions. Okay. So we first look at the region which is the peritectic region. So what we did was, we first looked at lead tin alloy, and now we are looking at iron carbon alloy phase diagram. So iron carbon, the first region is the peritectic region. Peritectic region, so if I just draw that particular line, it has basically what happens is that here you have liquid present here. This is at 1493 degrees centigrade, 97 or 93, let me check. It is 1493 degrees centigrade. So this is temperature axis. This is 0.1%, this is 0.15%, and this is 0.5% carbon. Okay. So in this, at high temperatures for pure carbon, you have this delta phase, of carbon, which has BCC structure. If you increase the temperature, if you increase the iron content further, this delta phase coexists with the liquid phase, and you can draw the composition of two phases. You can determine the composition using tie line. This delta phase and liquid phase, delta phase of composition 0.1% and liquid phase of composition 0.5%, transform into gamma phase, which is FCC phase of composition 0.15% through a peritectic reaction. So liquid plus delta transforming into gamma, liquid of composition 0.5, delta of composition 0.1, and gamma of composition 0.15. So in a peritectic reaction, the solid which forms has a composition intermediate to liquid and solid temperature, and the liquid composition is on one extreme. Okay. This is the identification of peritectic reaction. So this region is basically liquid plus gamma. Okay. So this is the peritectic region of the phase diagram, and you can see you can draw the microstructural development the way it happened in. So this is delta plus gamma region, and this is liquid plus delta region. If you look at the right part of the phase diagram, which is the eutectic part, In the eutectic part, you can see that we have liquid transforming into a mixture of gamma phase plus cementite at a composition of 4.3% and at a temperature of 1147 degrees centigrade. So, if I draw this eutectic region, so this is the composition 4.3%, this is 6.7, and somewhere here you have 2.1%. So, you have this is 1147 degrees centigrade, and of course you have these two lines coming from top from the peritectic region. So, you have liquid plus gamma, liquid plus Fe3C, which is cementite, and these two this converts into gamma plus Fe3C at this temperature. So, this is the eutectic reaction. So, liquid of composition 4.3% transforms into gamma of composition 2.1% plus Fe3C, which is 6.7% carbon basically. Now, here the difference between alpha, delta and gamma is delta is solid solution of carbon and iron at high temperature, and its solid solubility varies up to the limit of solid solubility. Similarly, gamma it has a BCC structure. Similarly, you have gamma iron, which is again solid solution, and it has a FCC structure, whereas Fe3C is called as cementite. It is not a solid solution, it is a line compound, or you can say it is intermetallic. It is much stronger than alpha and delta iron, it is very hard. So, comparatively gamma and delta and gamma are very soft phases. Fe3C is extremely hard, very hard. Okay. Now, the third part of iron carbon phase diagram is the eutectoid part. And this is the most important phase diagram. This is most important part of the phase diagram as far as engineering applications of iron phase diagram are concerned. In this part of the phase diagram, the gamma phase of composition 0.76%, which is solid phase, transforms into a mixture of alpha iron, which has very low solid solubility of carbon in iron, about 0.022%, plus cementite. So, what it does is basically, so it has, you have like this. So, this is the temperature 727 degrees centigrade. Okay. So, this is nearly 0.8%, this is 0.02%, and this goes all the way. The interesting part of phase diagram is only up to 2%. Okay. So, gamma iron, which is FCC, converts into alpha plus Fe3C, and this is pure alpha, this is alpha plus gamma, this is gamma plus Fe3C. So, the region which is left of 0.8% is called as hypo-eutectoid. So, less than 0.8%. The region which is right of 0.8% is called as hyper-eutectoid. And iron with carbon less than 2%, less than or equal to 2%, is called as steel. These compositions make up the modern material called as steel, and it is this part of the phase diagram of iron carbon which is extremely interesting for from the perspective of engineering this material for variety of applications. So, what you have here is you have single phase gamma, which is FCC structured. So, when you start in this region, you have these grains of gamma. So, this is gamma all. Now, depending upon whether you are cooling, from this point, whether you are in this point, whether you are in this region, you will obtain different microstructure. So, you can see that the microstructure is going to be fairly similar to what you obtain in eutectic. It's just that it's going to happen in solid state, and since it happens in solid state, the feature size is even smaller because the diffusion distances are smaller in solid phase. So, what you have here is you have this composition, 0.8% composition, which is called as eutectoid steel. Then we have less than 0.8%, which is called as hypoeutectoid steel, and then we have steel between 0.8% and 2% is called as hypereutectoid steel. And it is the three kinds of phase distributions which are important from the perspective of engineering applications of this alloy. So, and anything beyond 4%, beyond 2% carbon is called as cast iron. So, if your carbon content is between 2% to 6.7%, the alloy will be called as cast iron. If your composition of the alloy is below 0.8%, 0.76% to be precise, it is called as hypoeutectoid steel, and if it is between 0.76 to 2% carbon, it is called as hypereutectoid steel. So, this region is steel and this region is cast iron. Okay. And there are various phases. Liquid phase is present at high temperature. Delta Fe, which is a polymorph of allotrope of iron, is present at high temperature for very low percentages of carbon or for pure carbon. Gamma phase, which is the FCC structured phase called as austenite, this phase is present from, this has maximum solid solubility of 2%, 2.1% at a temperature of 1147 degrees centigrade, and it has very large single phase region starting from peritectic temperature of 1493 degrees centigrade to the eutectoid temperature of 727 degrees centigrade. So, this whole region is single phase gamma region, FCC structure, but this is unstable phase because it's a high temperature phase. This transforms into two phases at lower temperature. One is called as alpha Fe, which is called as ferrite. Alpha Fe is called as ferrite. It has very little solid solubility of carbon in iron. It is a soft phase of iron. And second phase which forms at low temperature is called as cementite, which is Fe3C, cementite. And it is the microstructure of these three regions which is of importance. So, microstructure of this region, microstructure at this point, and microstructure at this point, which is what is important from the perspective of engineering applications. And these microstructures can be tailored, modified quite extensively by adopting different cooling rates, etc. So, there are three invariant reactions that happen at 1493 degrees centigrade. Peritectic reaction occurs. Liquid of composition 0.5%, delta of composition and delta iron of composition 0.1% transform together to give gamma iron of composition 0.16%. This is 0. Okay, 0.16%. 1147 degrees centigrade, you have eutectic reaction in which liquid of composition 4.2% transforms to gamma iron of 2.1% and Fe3C, a line compound. At 727 degrees centigrade, eutectoid reaction occurs in which gamma iron of composition 0.8% transforms into alpha iron of 0.0002% solid solubility and Fe3C. These are the three major invariant reactions that occur in iron carbon phase diagram. Now, let us look at what are the microstructures that we obtain. If you have 0.8% carbon steel, which is 0.7, basically 0.76, eutectoid, we call it eutectoid steel, the composition for which the gamma phase, so eutectoid steel is the one. So, eutectoid steel is the one for which carbon content is in the vicinity of 0.8%. So, basically in this, the gamma phase converts into a mixture of alpha Fe, which has a solid solubility of 0.02% plus Fe3C. and this is a eutectoid mixture. It forms all of a sudden. So, you had started with grains of gamma, this is all gamma, and then you suddenly convert this into a mixture. So, you had these grain boundaries of gamma. On these grain boundaries of gamma, you have nucleation and growth of, so this is how they will form. So, these colonies will form. So, this is the alpha Fe plus Fe3C colony. This is called as lamellar structure of, and if you look at it microscopically, what it's going to look like, it's going to look like this. You have plate of, let me use a different color here. So, you have a plate of alpha, then you have, so these are the plates of alpha. So, you have alpha, in between you have Fe3C, and again just like eutectic, you are going to have partitioning of solute. So, alpha will release carbon, which will get into Fe3C, and iron will move from other side to make alpha Fe. So, this is Fe rich and this is carbon rich. So, that is why they form a parallel lamellar structure, and what you see in the micrograph is something like this. So, you see sort of grayish microstructure in which you can see these are the parallel plates. So, you have this as a parallel plate, you can see these are the parallel plates. Okay. So, you can see, and if you zoom it up, the microstructure, these are the parallel plates. So, you have plates of cementite parallel to ferrite. So, this is how the microstructure looks like. If you want a finer description of the microstructure, let us look at the next. So, this is a finer description of the microstructure. You have these parallel plates of alpha and Fe. So, alpha is the brighter phase. You can see that there is larger proportion of alpha than cementite. So, thicker plates will be that of ferrite and the thinner plate will be of that of cementite. And you can see this kind of parallel plate microstructure, lamellar microstructure that you will see, and this is called as pearlitic microstructure. The pearlite is not a phase, it is just a mixture of alpha Fe and cementite. So, in steel, this mixture of eutectic, mixture of the alpha Fe plus Fe3C is called as pearlite. So, as long as you have a microstructure which has this kind of morphology, which is lamellar morphology, the microstructure will be called as a pearlitic microstructure. And the microstructure of the other two sides will be very different, which we will look at in the next lecture. So, what we have done in this lecture is we have again looked at a few common phase diagrams such as lead tin phase diagram and iron carbon phase diagram. We have looked at the various invariant reactions in the iron phase carbon phase diagram, and also how the microstructure looks for a eutectoid steel. In the next lecture, we will further develop on it. We will look at the microstructures of hypo and hyper eutectoid steels as well as a few cast irons before we move on to the next part of the course. Thank you very much.